Hi everyone. Thanks for attending this TCS Plus talk. We're delighted to have Susanna Rezende tell us about lifting with simple gadgets and some applications to circuit and proof complexity. Susanna is currently at the Institute of Mathematics of the Czech Academy of Science. She was previously at KTH, where she got her PhD with Jakob Nordström and did a lot of very cool work in computational complexity and proof complexity. So we're delighted to hear more about that today. Before starting, I'd like to give a shout out to all the people behind the scene. So Eric right now is moderating the talk, and there is the whole TCS Plus team as well. And I would like to encourage you to suggest talks on our website if there's anything you'd like to hear about. Without taking much more time, Susanna, thanks again for speaking, and yeah, the floor is yours.
Thank you. Yeah, so I'd like to start by thanking the organizers for inviting me. It's a great honor to be talking here at TCS Plus, and also for the people on Zoom, please feel free to interrupt me at any moment. I'm usually not very good at telling whether people are following or not, and especially via Zoom, it might be a bit more challenging. So please, anything that's not clear, any questions, feel free to interrupt me at any moment. Okay, so my goal with this talk is to motivate people to this lifting technique. So that lifting is a great tool that can be used for proving lower bounds in many settings. So this is my goal, and this talk is based on a joint work with Robere, Jakob Nordström, Tony Pitassi, Robert Robere, and Mark Vinyals. Okay, so the plan for the talk today. So first, I'd like to motivate why we care about lifting, and I'll do that by talking about circuit complexity, and I'll also mention our circuit complexity applications from this paper. Then I'd like to actually say what lifting is and how it relates to circuits. I'll then talk about what our real motivation was in this paper for looking into this particular lifting, and that comes from proof complexity. And then I will explain where the title of the paper comes from, lifting with simple gadgets, and finally I'll end with some open problems. So first, circuits. So I'll be mostly talking about monotone Boolean circuits. So given a monotone Boolean function, so it's a function that receives some Boolean inputs and outputs either 0 or 1, and it has the property that for any input, if in some coordinates you flip the value from 0 to 1, then the output of the function can only increase. That's why it's a monotone function. So for example, the majority function is a monotone function. If I want to know whether the majority of the bits are 0 or 1, flipping it from 0 to 1 can only increase the value of the function. A monotone Boolean circuit is a DAG that has as inputs to the DAG the variables. The gates, the inner nodes of the DAG can contain either or and there are no negations, and it should output the value of the function it's computing. So this is a circuit that outputs the majority of 5 bits. Okay, if this DAG happens to be tree-like, then we say this is a monotone Boolean formula. So a natural question relating these two objects is are circuits more efficient than formulas? So is there some function for which there are small monotone Boolean circuits, but there are no small monotone Boolean formulas? So this was answered first by Karchmer-Widerson in 1990, where they showed n to the log n separation between monotone circuits and monotone formulas for the ST connectivity function. This was later improved by Raz-McKenzie, where they showed an exponential n to the epsilon for the gen function, which was a generalization of this ST connectivity. This was later on improved to exponential in square root n by Pitassi. And in this paper, we get nearly optimal separation of exponential in n over polylog. So I'd like to mention that except for the first result from Karchmer-Widerson, the other three results were proved using lifting. Okay, so this is the result relating monotone circuits and monotone formulas. Another type of circuit we can consider is monotone real circuit. So a monotone real circuit it's also going to compute some Boolean function, but the gates, they can be arbitrary monotone real functions. So let's look at an example. So here I have the circuit, the monotone Boolean circuit computing majority, and here I have a monotone real circuit computing majority. So you can see basically what it's doing is summing all the 5 inputs, and then there's a threshold gate, which is simply calculating whether the sum of all these 5 inputs is greater or equal to 3. Okay. And the gate is monotone if whenever I increase any of its inputs, the value of the gate can only increase. So if I fix one of the inputs and increase the other, the value can only increase. So that's what I mean by monotone gate, and it can compute any monotone real function. Okay, so we can ask the same question. Are real circuits more efficient than Boolean circuits? So it looks from this picture that actually we have a much smaller monotone real circuit computing majority, but it was shown that even there are polynomial size monotone Boolean circuits computing majority. So majority is not an example that separates these two models of circuits, but can it be the case that there is some function that separates this? So Rosenblum in '97 showed an implicit separation, and he actually showed that monotone real formulas, so even when we consider tree-like monotone real circuits, are exponentially stronger than general Boolean circuits, even non-monotone Boolean circuits. So this is an implicit separation, and the proof is simple, and it fits into the slide, so I would like to show it, and so I hope you can follow. So it's the following. We would first like to show that monotone real formulas can compute any slice function in linear size. So what is a slice function? So here I have the Boolean cube. On the bottom, I have the all zeros input. On the top of the all ones input. And any slice of this Boolean cube contains all the inputs with the same Hamming weight. So the same number of ones. So a slice function is a function that you fix some slice. Below this slice, anything that has smaller Hamming weight, the function will output 0. Anything that has larger Hamming weight, it will output 1. And for this slice, it can output anything. And note that this is indeed a monotone function because flipping from 0 to 1 can only increase the value, because either you'll leave the slice and then the value of the function is 1, or you'll be 0 and get into the slice, and that can only increase the value. So this is indeed a monotone function. So how do we see that there are monotone real formulas that compute this function in linear size? So here's the proof. So the idea is that you'll have the top gate of the monotone real formula will be receiving as inputs this gate G1 and this gate G2. And what you want is that G1 and G2 will both somehow encode the value of the input, but in such a way that G can actually monotonely compute F. So let me explain this right here. So suppose we have some x and y in my slice, and if I can guarantee that we're in either one of these cases. So we have either that G1 of x is greater than G1 of y, and G2 of x is smaller than G2 of y, or G1 of x is smaller than G1 of y, and G2 of x is larger than G2 of y. So for any x and y, different x and y that are in the same slice, if we can guarantee that this property holds, then there is some monotone G that can compute F given G1 and G2. And if we also have that X is encoded in G1 and G2. So this is because we just need G to be monotone, and this makes that any two inputs in the same slice are in this sense incomparable. One of them is larger and the other one is smaller for any 2 points in the slice. So the way to satisfy this property, there's a very, very simple G1 and G2 that actually satisfies this property. And so basically I'm summing 2 to the I for every coordinate xi. And here I would like to sum minus 2 to the I times the value of xi. So in this way, I can actually encode xi by one real number, and I can have this property. But in order for G2 to be monotone, I add this extra slack here of 2 to the n plus 1. So this way, G1 and G2 are both monotone, and I can actually have these two properties. Okay, so this is the whole proof of how monotone real formulas can compute any slice function in linear size. Okay, so now what's left to show is why are slice functions hard for general Boolean circuits. And remember, this is an implicit separation. So what we'll show is that just most slice functions require Boolean circuits of large size. And that's simply because there are so many slice functions. So if we just look at the middle slice, the slice for inputs that have Hamming weight n over 2, then there are 2 to the n choose n over 2 different slice functions, and there are not so many different Boolean circuits. So there we get our implicit separation. But as we know, proving explicit separations is much harder than proving implicit separations. So can we actually prove an explicit separation between monotone real formulas and general Boolean circuits? So, well, this would at least require proving a general Boolean circuit lower bound, and that seems that we're still currently out of reach. So what about between monotone real formulas and monotone Boolean formulas? Can we show a separation, an explicit separation there? And this is one thing that we show in this paper. So we show an explicit function f, and that has a monotone real formula of size practically linear, but every monotone Boolean formula requires exponential size. Okay, more about monotone Boolean. Oh yes, and this was obtained also via lifting. Okay, so now more about monotone
Susanna,
Yes.
what is your notion of explicitness in this result?
Explicit, that you can generate it in polynomial time. It's yeah, it comes from so we'll see where it comes from, this function. It comes from a partial function, and then you consider the monotone real formula that computes this partial function, and it actually computes some complete function, and that's the function you consider. So the partial function might be more explicit, but you can actually, since you can compute it in linear size, you can compute the total function too.
All right, thank you.
Okay.
I've got a small question about the,
yes.
the lifting technique. So you're saying that no proof of that was known before, and actually all the proofs of similar statements use lifting. Is it possible, once you've got that proof, to actually unroll the sequence of arguments to get like a direct proof, or does that become completely horrendous or impossible to do?
For what result? For this one or the previous?
Either. So yeah, if I wanted to say like, here's the comparable direct proof of this statement, I'm just going to take the proof through lifting and just, well, open up every single aspect and see if I can get that directly. Is that feasible, or does that sound absolutely horrible?
Yes. I mean, I guess you could, but it would just be you will just be, so actually Raz Mackenzie for this so where do I have, yeah, this result, they don't prove, well, they don't explicitly state the general lifting theorem, but they're actually, that's what they're doing, and that's actually I don't have the reference here, but it's goes Pitassi Watson. They state the general lifting theorem. They do it specialized for their application. So you could, in that sense, specialize it for your application. But I'm not sure whether you would say that's not a lifting theorem. It seems, yeah.
Thanks.
Yeah, I don't know. Okay. Yeah, thanks for the questions. Okay, so, right, so what other monotone Boolean circuit classes can we consider? So we have, well, MP is the class of all polynomial size monotone circuits. Then we can consider what if we restrict the depth of the circuits, right? And we get the class ACI, which has depth log to the I. Then we can also restrict the fan-in of the circuit. So before I didn't say this, but we could have unbounded fan-in and the class NC to the I, we only considered bounded fan-in. So clearly we have this sequence of containments. And actually we also have that if we go one layer below, monotone ACI minus 1 is contained in monotone NCI. So we have these containments, but are any of these equal, or can we separate these? And actually for all of these, there are separations known, and all these separations were proven via lifting too. Okay, so I hope I motivated you how lifting can be useful for proving lower bounds and separations. So now let's see what lifting actually is. So lifting, it's a method of transferring lower bounds for some weak computational model to some stronger computational model. So for example, decision tree. So this is a tree where I'm querying the variables, and at the leaves, I should determine the value of the function on this sequence of variables, the queried variables. So this is a weak computational model, simply querying, and I should determine the value of the function. A strong computational model would be, for example, communication. So here, Alice, so we have two players, Alice and Bob. They each receive part of the input. So Alice receives X, Bob receives Y, and they can only see their part of the input, and they have to communicate to compute some function that depends on both X and Y. And their goal is to figure out the value of this function while communicating the minimum possible. So this is a much stronger model. And okay, so how do these two actually relate? So here, Alice and Bob, they communicate via some protocol. And the protocol also looks like a tree. So they start at the root of the tree, and it's labeled by whoever speaks. And then according to whether Alice says 1 or 0, they go either left or right. And then maybe Bob speaks, and so on. And at the end, they should output the value of the function. So these things at least have a similar structure. And what the lifting theorem does is to show that the query complexity of f is less than the communication complexity for some related function, f prime. So if you can prove a lower bound for f, for the query complexity of f, you actually get a lower bound in a much stronger computational model. So that's why it's a powerful technique, because now you only need to prove a lower bound for the weaker computational model. Okay. So I will refer to query complexity of f as Q of f and communication complexity as CC. Okay. So let's look into a bit more what lifting theorem does. So one common lifting theorem, the function f prime is actually f composed with some other function, which I call gadget, some gadget g. So this composition works like this. So if f receives as input some z1 up to z5, then f will receive as input 5 copies of g, and each g will receive as input some x and some y. So this is what I mean by f composed with g. I'll sometimes omit the superscript n. So from this, it's not hard to see that the communication complexity of the composed problem is not more than the query complexity of f times whatever it takes to figure out the value of g. And the reason is that Alice and Bob, they can simply simulate this decision tree, and every point they want to figure out the value of some inputs, they just calculate g, compute g for that input. So that takes CC of g, and then the query complexity is the depth of the tree. So, and communication complexity is also the depth of this protocol. Okay, so let me show you some of the gadgets that have been used to prove these lifting theorem. Oh yeah, and the lifting theorem, they're basically showing that this is the best possible, right? So that actually the inequality also holds it the other direction. That's what a lifting theorem shows. So some of the gadgets that have been used. So the indexing gadget. So the indexing gadget, Alice receives some pointer. Bob receives a very long array of 0 and 1s. And the way this gadget works is that simply what Alice is pointing to in Bob's array. So the 5th input in Bob's array is 0, so that means that this indexing on the first coordinate gives 0, and so on, and the second coordinate 2, and the third gives 1, and then the third coordinate it gives 1. So this is the indexing gadget. Another gadget that has been considered is the inner product. So here, it's an inner product mod 2. So Alice and Bob receives us some rows, and they're just computing the inner product of their first row gives 0, the inner product of their second row gives 1, mod 2, and so on. So these are two of the gadgets that have been shown that you can obtain lifting theorems. So this is a way of proving the lower bound for decision tree and obtaining the lower bound for communication complexity. But I said this is related to circuits, so how is this related to circuits? So there's what is called the Karchmer-Widerson game. So here we're given this monotone function f, and Alice receives some input in the preimage of 1. Bob receives some input in the preimage of 0. And since it's a monotone function, there must exist at least one index, I, such that x of I is greater than y of I. Okay. So their goal is to communicate to find such an I. So how does this relate to circuits? So here we have a circuit computing some function f, and here we have a protocol for Alice and Bob. So given a circuit, we can create a protocol that has exactly the same structure as okay, I'm considering tree-like now for simplicity. So that has exactly the same structure as this formula. And for every OR node, we're going to have Alice speaking. For every AND node, we're going to have Bob speaking. So let's see why. This Alice's input is in the preimage of 1. And here we have an OR function. So that means that for Alice, at least one of the inputs to this OR gate has to be 1 in order for this OR gate to output 1. For Bob, he has an input in the preimage of 0, so that means that both of the inputs to this OR gate has to be 0. So if Alice tells Bob which direction she has a 1, they can move on to that part of the circuit, and now they still know that whatever function is computed in that part of the circuit, Alice has a 1 and Bob has a 0. And the same holds in the other direction for Bob. If wherever there's an AND, since Bob has a 0, at least one of the inputs is 0, and since Alice has a 1, both of the inputs is 1. So if Bob says where his 0 is coming from, they can move to that direction. And finally, when they reach a leaf, it's actually some variable, and we know that for that variable, Alice must have a 1 and Bob must have a 0. So that's an answer to the communication problem they're trying to solve. So given some formula, Alice and Bob can come up with a protocol with exactly the same structure that solves this Karchmer-Widerson game. Okay. And actually, the other direction also holds. Okay, so let's look at some lifting theorems. So we have the Raz-Mackenzie lifting theorem, which was made more explicit in Pitassi-Watson. So here we have any f can be any of total function, partial function, or relation. For several applications, we're interested in lifting theorems that holds also for relations. So they show that the communication complexity of f composed with G is greater than the query complexity of f times the communication complexity of G. Okay, but this only holds for some specific gadgets. So for G equals the indexing gadget, and that it has large size. So in particular, the communication complexity of the gadget that they require is log n. Okay. So this is this is a very, very nice lifting theorem. We would be happier if we could have it worked for smaller gadgets. Unfortunately, it only works for larger gadgets. Okay, then we have this other lifting theorem, which does not hold for query complexity. It holds for some other measure. This has to do with block sensitivity, and it also holds for every partial. Oh, sorry. This should say every partial function or relation. It holds only for some specific gadget, but of constant size. So that's a very nice feature of this lifting theorem. And the only let's say not as nice feature is that this measure is actually strong. It's a stronger measure than query complexity. So it's harder to prove lower bounds for this measure. So for lifting, the ideal scenario is when we can lift very weak measures to stronger measures. And then we have this Pitassi-Robere theorem, lifting theorem, where they have, I'll talk a little bit more about this later, it's some other measure, NS of F. And the interesting thing here is that, well, it only holds for some relations, F, but it holds for many gadgets, many different gadgets, not only for some specific gadgets. But it still requires some large size. Okay, so let's look a bit more at this Pitassi-Robere lifting theorem, because that's what this work is based on. So in order to do that, we have to define what the search problem of a formula is. So here a formula is just going to be a disjunction of clauses. And let's say we're given some unsatisfiable formula, and the search problem of this unsatisfiable formula is to find, given us an assignment to all the variables, find some clause that is falsified. There must be at least one clause that's falsified. Okay, so what Pitassi and Robere showed is that, so they showed two things: the communication of this search problem composed with a gadget. So this holds for any good gadget. So this includes several gadgets, but it has to have large rank. This is just the rank when you look at the gadget as a matrix. Then we get a lower bound of this type. And in the special case where we have a very large measure, so nearly the best possible, so linear, then we can actually even use some constant size gadget. Okay, so this NS measure is actually the Nullstellensatz degree required for refuting F. Just in case you know what that is, but it doesn't really matter for this talk. Let's just consider it as a measure of F. So if we look at this, it kind of suggests itself that there should be something more continuous between these two. Here we require very large gadgets, here only constant size gadgets. What about something in between? So that's what we showed, that actually there is something continuous there if you look closely at their theorem. And basically what you have is, so you do have the Nullstellensatz degree of for refuting F times this log factor. So you can see how these two follow from there. So in case the rank of G is at least n squared, then here you will get at least, so the one n will cancel with the n in the denominator, and then you'll get at least log of n. And in the case where the Nullstellensatz degree of F is n, then rank of G can be constant, and we still get greater than Nullstellensatz degree of F. Okay, so we first proved this continuous. I'll talk more about this later, but another improvement was that we showed that this holds for any gadget, not only for good gadgets. But for now, this is not important. So only with this continuous improvement, we can get this corollary of separating monotone circuits and monotone formulas almost optimally. Okay. So now in order to talk about why we're interested in having this for any gadgets and even why we cared about real circuits. So we were asking, are real circuits more efficient than Boolean formulas? Why do we care about real circuits? And the reason comes from proof complexity. So yes?
I have a small question about the previous
Yes.
slide.
Yes.
So the corollary, what exactly are the parameters you use to get that corollary? What is the rank you use for that?
Good question. Good question. Right. So there is a formula that is related to this gen function I talked about, and it has Nullstellensatz degree n over log n. Okay. So if you think of Nullstellensatz degree here is n over log n, then it's enough to have rank G equals log n in order for this still to give you a lower bound. So that's what we use. So we use any actually can work for any gadget that has rank log n, and then you'll get this.
Thanks.
Okay. So okay, so real circuits. So why do we care about real circuits? And this comes from so the real circuits were defined because of cutting planes. So the cutting planes proof system. So the cutting planes proof system, just a very quick definition. So we're given a set of unsatisfiable linear inequalities, and we would like to somehow use these linear inequalities to derive that 0 is greater or equal to 1, which would mean that these inequalities have no 0, 1 solution. And we're allowed to do some specific operations. So for example, let's say these are two linear inequalities in my set. I can add these, or more generally take any linear combination of these. So here I'm adding these. I can also take some linear inequalities that for every variable that it's greater than 0 or less than 1. So here I'm also adding these two. And then there's one rule, which is actually what is only sound over integers. So it's the division rule. So from this 2x plus 2z greater or equal than 1, since x and z are integers, this actually means that x plus z is greater or equal to 1. So it doesn't really matter what the rules are. They're sound rules. What matters is that we're dealing with inequalities. And here we say the length of the proof is simply the number of nodes in this stack. Okay, and then we have two other measures that we care about. So the space is simply the memory you need, the number of inequalities you need to keep in memory in order to verify the proof, but also the coefficient size. So here the largest coefficient is 2. In general, you can have proofs with larger coefficients. There's no restriction on the coefficient size. But a natural question is, are large coefficients actually necessary? Can small coefficients simulate large coefficients? And actually, Buss and Clotet studied this question, and they actually wanted to show that coefficients of polynomial magnitude are enough. So CP stars is cutting planes with polynomial coefficients. So they wanted to show this. They were able to show that exponential suffice, but not polynomial. So we still don't know whether polynomial magnitudes suffice. And it's interesting that all the lower bounds that we can prove, we can actually prove for cutting planes with large coefficients. And most upper bounds, they hold for small coefficients. So that would make you think that maybe these two things are equivalent. There have been some more recent results where they actually use these large coefficients. So then here we have this question, well, are these large coefficients actually necessary for, we don't know. So the question we were addressing was, can we actually separate these two proof systems? Maybe cutting planes with large coefficients is actually stronger than cutting planes with polynomially bounded coefficients, with regard maybe to length or to space, or even some length space trade-off. And that's what we showed, that there is some formula F that has cutting planes refutation in polynomial length and constant space, but any cutting planes refutation with bounded coefficients, so if it has length L and space S, then it must hold that S log L is at least N. So this is saying that either you're using some polynomial, almost linear space, or if you want to restrict your space, you're going to need exponential length. Okay, so this is a formula where if you bound the coefficient, you can't optimize both space and length at the same time. But if you allow large coefficients, then you can actually optimize these two. Okay, so this is a trade-off separation. So how does this relate to communication? So we also prove this via some lifting theorem via communication. So this works as follows. So if we're given a proof, so let's say this is the cutting planes proof we were looking at, then Alice and Bob, they want to solve this problem where it's a search problem, except now we're talking about linear inequalities. We have a set of unsatisfiable linear inequalities, and Alice and Bob should find some falsified linear inequality from the set, given an assignment to the variables. And the variables are split between Alice and Bob. That's why they have to communicate in order to find this falsified linear inequality. And they can use the proof to help them find this. And basically, they know that whatever assignment they have, it falsifies 0 greater or equal to 1. And they would like to follow some path in this proof until they find some inequality that is falsified. So they would always like to keep the invariant that whatever path they're following, their combined assignments falsifies the inequality there. So for example, if this was obtained by adding these two inequalities, they would have to see whether is it true that their assignments must either falsify explicit greater or equal to 1, or it must falsify minus x minus z greater or equal to 0, since this is a sound step. So in this way, they can reach some falsified inequality. Okay, but in order to do this, they have to be able to communicate and figure out whether their assignment actually falsifies an inequality. And in the classical communication model, if they're looking at an inequality with very large coefficients, this would require many bits of communication. So if the coefficients have magnitude 2 to the n, they would have to communicate at least n bits, and that's too much. But if we only have coefficients of polynomial magnitude, then they only have to communicate log n bits. So if we wanted a model of communication that could actually compute an inequality efficiently, that's where the concept of real communication came into, which relates to the real circuits we were talking about. So real communication is the following. So Alice and Bob, they don't talk to each other directly. There's some intermediate referee, there's some oracle, and they send any real number to the oracle, and the oracle answers whether Alice's input is greater or equal to Bob's input. So answers 1 if Alice's input is greater to Bob's input, or 0 otherwise. And we only count the communication according to what the oracle says. So in this way, they can actually evaluate an inequality with 1 bit of communication. So they can simulate the cutting planes proof with every step with 1 bit of communication, even if they're large coefficients. So, okay, so if we're trying to separate these two, cutting planes with large coefficients and cutting planes with small coefficients, let's look at the lifting theorems that we mentioned before. So we had the Raz-Mackenzie lifting theorem, and the thing is that they've been shown to also hold for this real communication model. So these gadgets indexing inner product, they are hard even in this real communication model. So let's see. So here I have some decision tree. Via this lifting, I can get a lower bound for communication, the classical communication, and from here I can get a lower bound for Boolean formulas, or for, let's say, cutting planes with bounded coefficients. But I will also get a lower bound for this stronger real communication model, and from here I'll also get a lower bound for real formulas and tree-like, well, cutting planes with unbounded coefficients. So I can't use these lifting theorem to separate these two, because any lower bound I get for in one setting, I'll also get in the other. So the problem is that these gadgets, they're too hard, and we need some intermediate gadgets, some Goldilocks gadgets. So something that is hard for classical communication, but is not hard for real communication. So what can real communication do that classical communication cannot? Right? We have a greater than oracle, so it can definitely compute greater than. With 2 calls of the oracle, it can compute whether 2 numbers are equal. It can compute equality. So these sound like some good gadgets that could actually separate these 2 models, greater than, equality. So if we go back to the Pitassi-Robere lifting theorem, this is why we wanted it to hold for any gadgets, not only for good gadgets, but for any gadget, so that it would also hold for equality and greater than. So I'm almost finished. There was one technical step that we needed in order to prove this for any gadgets. I won't get into it. I'll just, it was something about the rank of matrices in gadgets, and yes, and then there was proof that fits in this slide almost. Okay, but now let's compare. I'd like to compare these lifting theorems. So on the one hand, this Raz-Mackenzie and Pitassi-Watson lifting theorem. So this holds for any relation R, any relation partial function, total function, and it holds only for some specific gadgets G. And the Pitassi-Robere lifting theorem, which we generalized, it holds only for some specific relations R, but it holds for any gadget G. So here we talked about the indexing gadget. This has also been generalized to hold for some other specific, like inner product, some other specific gadgets. This only holds for relations of the type search F. And here we have a lifting from query complexity, and here we have a lifting from Nullstellensatz complexity. But what I wanted to point out is that this holds for any relation, but only some specific gadgets, and here this holds for some specific relation, but only for but for any gadget. Okay. So okay, so now just to conclude, so in this paper we actually I'd say we squeeze out everything that was already there in Pitassi and Robere's lifting theorem. So we just see like how far can we push it, and then we get this more general lifting theorem. And this is what gives us these the two circuit complexity separations we talked about, separating monotone Boolean circuits from monotone Boolean formulas, and separating monotone real formulas and monotone Boolean monotone Boolean formulas. Also getting this proof complexity separation, this length space trade-off separation for cutting planes and cutting planes with bounded coefficients. And then some open problems. So I think for proof complexity, there's this very interesting open problem of separating cutting planes with unbounded coefficients and cutting planes with bounded coefficients with respect to length. So this is still open. I said that many of the monotone circuit complexities separations were known and were proven via lifting. They're not optimal, so also improving the lifting theorems for smaller gadgets would also improve these separations. It's also open to obtain some explicit separation between monotone Boolean circuits and monotone real circuits. So we only showed it for formulas. So for circuits, it's still open. And then a more open-ended question would be to a better understanding of inner and outer functions in lifting. How do these relate? Okay, that's it. Thank you. So any questions?
Thanks, Susanna, for the very nice talk. So I have a question about the case of monotone circuits. So what happens when you try to extend your proof, your separation from formulas to circuits? What is the technical issue?
Right. So if I go back to this lifting theorem, so this lifting theorem of Raz-McKenzie equals Pitassi-Watson, this has been generalized for DAG-like communication. Which is what you need in order to prove things for DAG-like objects. For this Pitassi-Robere lifting theorem, it's not of the same type. It doesn't actually prove the lower bound via this simulation theorem that is used here. So it actually proves the lower bound in this Rasburov rank measure, which in turn lower bounds communication complexity, but only in the tree-like model. So it's not clear how to generalize this for DAG-like, and I think it's a very, very interesting problem. Like, can you lower bound maybe some other measure that actually lower bounds the DAG-like communication? Yeah, so I guess that's the main issue.
I see. Thanks. And another question, your separation is nearly strongly exponential except for some polylog n's.
Yes.
Is there any chance you can shave off this polylog n's, or is there something inherent?
So there is something from this method that we use, the formulas that we consider, the Nullstellensatz degree, there's an upper bound of n over log n. So we would need, if we were to use this lifting theorem, some formula that such that the Nullstellensatz degree is exactly n, but at the same time it must be computed by polynomial size monotone Boolean circuits. So at least the strategy that we've been using, even if we had like constant size gadget, we would still have a lower bound of n over log n and not of n.
I see.
So we would have to find some other formula. Yeah.
Okay. Well, thanks, Susanna. I'll take us offline now. We can still hang out and like ask any remaining questions, but Yeah, so I'll take us offline right now.
Okay, perfect.